You're lazy. You're dumb. You're useless.
Geez, he's such a critical angle. Okay, so in the last lesson we looked at Snell's Law, and we looked at situations like this where we had light coming into another medium, in this case going through air into water. Now in this case the n value is 1 in air, and then it's going into a higher n value or a higher refractive index, and so we saw that this would cause the light ray to bend towards the normal. Then when it exited out of the water in this case and went to a refractive index lower, so now it's going from 1.33 back into 1, we saw that it would bend away from the normal. But now let's take a look at what happens to that refracted angle when we change the angle of incidence. When going into a higher refractive index, we could rearrange Snell's law into this equation. And at the end of last video, we put in 45 for the angle of incidence and got the angle of refraction to be 32 degrees. But now let's see what happens when we increase that angle of incidence and get an arrow like this. Well, that means that this angle is going to be approaching 90 degrees. That's as big as it can get. So as that increases to approach 90 degrees, sine 90 is equal to 1. So I'm just going to put a 1 there. Then I take inverse sine of 1 over 1.33, and I would get a value of 48.8. So then my refracted angle would look like this, 48.8 degrees. So that's the max value that we can have for the refracted angle. Now let's look at the opposite, where we decrease that angle of incidence. I've switched the arrow above. Now that angle is going to be approaching 0 to the normal. So my line is going to look more like this. I didn't draw it quite perfectly perpendicular, but it's getting close to 0. As that gets close to 0, this whole number gets close to 0. And when I take the inverse sine of 0, I would get a number of 0. So that means as I approach 0 degrees here, I also approach 0 degrees here, which makes sense. If we shoot light directly down into water, it should continue on in a straight line. So not too much interesting there, but now let's look at when it exits the water and goes into the air. So now in Snell's law, I flip my refractive index. I'm starting in 1.33 and going into n is equal to 1. So rearrange Snell's law, I would get this equation here. And let's start in the middle. If I plug in about 45 degrees here for my angle of incidence, 45 there, I would get a number of about 70 degrees coming out here. But now let's play with that angle of incidence. If I decrease that angle of incidence, then I'm going to start getting closer to this line. Similar to what I just saw before, I'm getting close to straight up and down. What does my angle of refraction get close to? Well, again, this number of sine approaching 0 is going to become a value of 0. 0 times 1.33 is 0, and we should get this approaching 0 as well. And this makes sense. If it's coming directly down out of the water, we would expect it to go straight into the air. But now comes the interesting part, and it's going to be the focus of our lesson. If I switch this to increasing my angle, so my arrow is going to look more like this, approaching that 90 degrees, what's going to happen to my refracted angle? Well, the max that this angle can be is 90 degrees. So as this approaches 90, this value is going to approach 1. 1 times 1.33 is 1. And when we take inverse sine of 1.33, we get an error. Why is this happening? Well, how we've been using sine and cos in this course is for angles that are within 90 degrees. So for example, if we had an angle going like this, we've often found the x and y components. We would find the x here and the y like that. Now we use sine to find that opposite side. So for example, sine of 30 gave us a number of 0.5. So for example, if this hypotenuse was 100 and we took sine 30 times 100, we would get a number of 50 here. And that's because the number sine 30 was equal to 0.5. Sine 30 is equal to 0.5. So we multiply the 100 by sine 30, or 0.5, and got a number of 50. And that worked for all angles in here. And that's because if I had something directly on the x-axis, sine of our angle was equal to 0. There was no y component. And if it was directly straight up, sine 90 is equal to 1, because all we had was a y component. But now in this last example, we had sine of our angle is equal to 1.33. So to be greater than 1 would be somewhere over here. This is looking at a place where our angle is going to be greater than 90 degrees. So back to the drawing over here with the water tank, this is 90 degrees to the normal. It would be straight, flat across the surface of the water. If it's greater than 90, that means it's going to be going back in the water. And that's our topic for today. That's when you have a ray going to a lower refractive index, that it's going to bend away from the normal so much, then it's going to go back in to the same medium and is just going to reflect. So some rays are going to reflect and other ones are going to refract. To determine what's going to happen, we want to figure out this middle point, which was when their incident ray is going to come in and the refraction is going to cause it to go right along that line of 90 degrees. In our formula up here, this is where our refracted angle is 90 degrees. And any ray with an incident angle greater than this, like this green line, we can see a greater angle to the normal line, that's going to reflect back inside of the water. Then we would look at those angles as angle of incidence is equal to angle of reflection, as we saw before. So determining the incidence angle that gives us a refraction of 90 degrees is important, and that angle is called the critical angle. So putting that in your notes here, it says that the critical angle is the incidence angle that when passing to a lower refractive index, so going to an n value lower than what it originally was, creates a refracted angle of 90 degrees. And again, I'll show that with the yellow line, comes in like this, going into a lower n value gives 90 degrees. This angle measured right here, that's the critical angle. And this means that anything greater than that critical angle will completely reflect. This is called total internal reflection. So I'll draw that with some green lines. We have one slightly bigger, it's going to reflect. A little bit bigger, it's going to reflect, and all of these angles greater than the critical angle are total internal reflection. So let's try an example question that says, what is the critical angle of a red laser passing from water into air? Pretty much what we've been talking about here. So we're going to solve this really similar to last lesson using Snell's Law, which I've put here. Again, I put R and I instead of 1 and 2. You might see 1 and 2 on your formula sheet. I'm going to plug in my numbers. So the refractive index that we're going into in R is 1, that's for the air. 1.33 is for the water. And I know that the angle that I'm going to get after refraction is going to be 90 degrees. So now I'm just going to rearrange for my incidence angle or my critical angle like this. And I've just taken sine 90 times 1, which is sine 90, and then that's divided by the 1.33, and then inverse sine to get rid of that sine right there. When I plug that into the calculator, again, sine 90 turns to 1, so this is inverse sine of 1 over 1.33, and I'm getting a number of 48.8 degrees. Okay, so that's all that we have for today. I hope that lesson helped you to understand critical angle and total internal reflection. Make sure you go give those practice questions a try, and I will see you in the next video.